Hello, everyone. My name is Han-Lee, a professor of Korea University. I'd like to thank you, everyone, who participated in the material science session of the second Korea-Sweden R&D Network Day. We have a total of 6 speakers, 3 from Korea and also 3 from Sweden side. So we will have a presentation each side, and then we will discuss and share our research and research experience. Let's first start with the Swedish side. Professor Thomas Swan, director of the MIFAB at Chalmers University of Technology. MIFAB or MyFab?
So, thank you very much. I will give you a brief presentation of MIFAB or MyFab, which is a Swedish research infrastructure for micro and nano fabrication. And fabrication is a key word here because it's basically a really big workshop, and that is open to researchers and entrepreneurs in Sweden and also from other countries. And it is a distributed infrastructure. We have 4 laboratories in 4 cities in Sweden, in universities, and it's based in clean rooms. And in the clean rooms, we have a lot of equipment, the best we have in Sweden, as well as expert support. So it's intended for advanced research as well as for education. And the users come, they are researchers as well as people from industry and institute, which are engaged in product development. And to have access in a smooth way, we have set up an electronic system we call MIFAB LIMS, which presents the laboratories and the tools at all the sites. And now I would like to show you some movies that you can see the real world MIFAB here, just in a second.
MIFAB provides access to the best nanofabrication facilities in Sweden. Our cleanroom labs are located at 4 major universities: Uppsala University, KTH in Stockholm, Chalmers in Gothenburg, and Lund University. We enable one single entry point to all 4 locations and give access to state-of-the-art resources and equipment.
MIFAB was started with the intention to open up the Swedish cleanroom facilities to researchers, to entrepreneurs, to existing companies, and to students. This to benefit research, development, and education.
Individual user access enables researchers and engineers to plan and carry out work themselves on site, with all available equipment. Education and training is provided to let users get the most out of our facilities and to keep exploring new possibilities. Process service is ideal for companies and startups, nanofabrication or process work in smaller batches, perfect for R&D work.
Now, with a 10-year perspective, it's very nice to see that many of the original intentions has been fulfilled. MIFAB has contributed in a very nice way to internationally recognized research results, as well as to the competitiveness of companies that have used the facilities.
Get in touch today and realize your nano vision.
Okay, this was a way to let you travel virtually to the 4 clean rooms in Sweden. And now I'm going to present some details about the infrastructure. Altogether, we have more than 700 instruments located in the labs. And last year, we have statistics for 836 active users, actually people, researchers that go in physically in the clean room and do some work there. They are usually connected to a larger group outside of the clean room. And this is very often the start of a value chain where devices or structures are manufactured and then set into a larger system. Altogether, these users come from either university or about 100 companies or institutes. In the 4 laboratories, we have 78 persons or engineers or experts working. 1/3 of them, about 24, have a PhD axim. The total area is 5,400 square meters, so we have plenty of space. And the Research Council, they have a grant for us to have this service as a national research infrastructure every year for more than 10 million euros. And the total turnover is more than 22 million euros last year. And the number of hours worked in the clean rooms comes basically from research, 85%, and commercial hours is about 15%. The 4 labs have a lot of things in common. They have the clean rooms and the skilled staff, but they also specialize in certain areas with certain equipment and certain skills. These are local expertise areas which connects very closely to large and skilled research groups. And I give you a short walkthrough through the labs. Chalmers University in Gothenburg, they have expert profiles in microwave and photonic process lines, as well as in nano and quantum technology processing. In Stockholm at KTH, they are experts in silicon CMOS and MEMS technologies in the process lines, as well as wideband gap technologies and optoelectronics. Lund University in the south specialize on epitaxy, nanowires, ALD and aerotaxy technologies. They have special equipment for Talbot displacement, lithography, as well as nano imprint. And Uppsala, close to Stockholm area in the Ångström laboratory, they focus on material science, various aspects, as well as thin film technology, surface science. Biomedical engineering is particularly strong there, as well as research on power generation and storage, solar cells and such, as well as silicon nanoelectronics. That's basically future devices. It has a large impact. We see over the previous period of operation, over the 4 years, 2016 to 2019, the researchers have produced almost 3,000 peer-reviewed publications, and 227 PhD students made their exams based on work performed in MIFAB. And we also monitored what comes out for utilization from MIFAB, and over a typical 5-year period, between 20 and 30 startups emerge. And and this is very much due to we have an open access, basically always open at the 4 locations. And since we have a lot of tools and we are able to handle the booking and the administration of the booking very efficiently through a LIMS system, we basically have no waiting time. There is no second selection because research, they already received the grant, and industry, they are also welcome basically immediately, provided you have the skills. And we also educate the users, giving introductory courses to clean work, as well as specialized training for special tools. We call it driver's license for specific tools. We help with process planning, as well as also in some cases also through process service for the users. And the LIMS system has been really a success story for us. We were starting to develop the system for our own users many years ago, more than 10 years ago. And this is basically a way to implement an open access model for users in an electronic tool. So it's used in Sweden at all of the labs, all of the MIFAB labs today, as well as more than 30 other academic labs. And other countries saw that this open model for access to nanofabrication was a very good way to handle it. So we have provided MIFAB LIMS and collaboration with other infrastructures in Norway, in France, in Finland, in Ireland, and in Portugal and Spain, as well as in Latvia. They share similar challenges, and they provide open access in a similar way as MIFAB. So they have now the MIFAB LIMS system to organize their activities over a license agreement. And we have a lot of users. From last year or from the year before, we have accumulated some statistics here. And last year we had 836 users, and we can get a lot of statistics, and also we can then forecast the development and see where we have to invest in new equipment based on the usage of the infrastructures. So I will now, in the remaining minutes, show you some outstanding results. I will just give you a few examples because time is limited, but we have research carried out in a broad range of scientific areas. And MIFAB has been very fundamental for some of the really large European projects, like the flagship program in graphene, as well as quantum computers in Europe. And we do research and we fabricate materials, structures, devices, and even small systems in MIFAB. And they are very much cross-disciplinary studies. The key enabling technologies are many of them present and available through MIFAB. And altogether, the United Nations 17 Sustainable Goals are, we support them, or the researchers support them very well, many of them through the activities. So in the next slide, just a few examples. Here is one very important research project. It's within the quantum computer project at Chalmers, where a special device which is intended to develop a new algorithm, a quantum QAOA algorithm, which is a combination, it's a hybrid quantum and classical algorithm to make an optimization. And this is a physical device made in MIFAB. And this is part of the Wallenberg Center for Quantum Technology, which is financed through the Wallenberg Foundation over more than a decade now. Moreover, to interface quantum structures as well as many other systems, you need very high performance electronics. And at Chalmers, they have developed world-leading low noise amplifiers. And also they have a spin-off company, Low Noise Factory, that provides the amplifiers to industry and to researchers. And here we also, through the Eurostars project, we have a very nice example of bilateral collaboration, Sweden and Korea, South Korea, through the researchers in the project. And these amplifiers have been used all over the world, also in some demonstration by Google and other, Google, they made a demonstration on quantum supremacy in 2019. So we move on. In Uppsala, here's an example on a nanopore device used for rectification of ion and molecular transport. They can control the size down to 5 nanometers, and they can basically select and separate single molecules for analysis with these small devices. As well as they have developed field effect transistors for charge sensing, then can detect biomolecules in extremely low concentrations. I see time is limited, so I go a little quick here. There is a spin-off company, Astrego, which use microfluidics to test which kind of antibiotics which is most efficient to treat, for instance, sepsis in a patient. This is a parallel design, so many antibiotics are tested in parallel in a single device here. In Lund, we have a new technology based on 3,5 nanowire arrays. These are made from small grains of gold, which at MBE, created by MBE, by EBL, and they grow these wires and get a lot of very high performance for the specific power. That means the power divided by the weight of the solar panels. Also, this is an example of nanowire structure where quantum dots are formed. They are connected and they are confined, but they are connected, coupled through strong G factors. And this is one way that could be used for spin-based qubits, also for quantum computers, as well as for spin filtering. At KTH, they have a very interesting technology for heterogeneous integration with CMOS technology. This is tailor-made and developed because one wants to integrate several sensors, biosensors, chemical sensors, energy harvesters, and so on, optical components onto CMOS, to a CMOS platform. And this is a technology in-house, which is currently developed and will be available to all MIFAB researchers. That's good track records, by the way. We have a lot of visitors from Korea, and this is just 3 examples of PhD students, former PhD students, which now have a very fruitful career in Korea after made their PhD in MIFAB, in this particular case in wideband electronics in Stockholm, supervised by Professor Mikael Östling. Then finally, an infrastructure needs collaboration and develops faster with good collaborations and network. And to have this option to collaborate with Korea is very, very interesting. We are also having a lot of experience from collaboration in the Nordic countries. We are part of the Nordic Nanolab network, all the 5 countries and their 12 labs builds this network. We have an expert network with 5 different groups, topology areas, concentrating on certain aspects of nanofabrication, dry etching, thin film, and so on. We arrange every 2nd year a big Nordic conference for the users and researchers. That's now next year we have to delay this 1 year because of the COVID-19. And together with researchers in Europe and in the Nanolab, we have another conference we started a few years ago on infrastructure questions on fabrication and on management on large infrastructure for nanofabrication. And finally, we are part of the Nanolab. And I think that concludes my talk here. I'm 1 minute or so over time. I thank you for listening. And I also like to welcome you to MIFAB because we provide open access and we will be happy to have visitors coming and collaborate with us. Thank you very much.
Thank you very much for excellent presentation, Professor Swan. And next speaker is myself. The title is Ultra High Refractive Index, Nanomolding Materials for Metal Lens. Hi everyone. My name is Professor Hon-Lee, Korea University. Today's my topic is Ultra High Refractive Index, Nanomolding Materials for Metal Lens. Here is a brief explanation about myself. Currently, I'm working on zero-energy radiative cooling materials and also nano-imprint-based high-efficiency metal surface. And here is the content of my presentation. I will explain to you about the metal surface and nano-imprinted lithography. Then I will discuss about the current experimental result. Then I'll summarize it. Well, what is a metal surface? Metal surface is a black box which can control the light as we want. At each point, output amplitude and phase are determined by the shape of each nano antenna. And many applications, including lens, hologram, or clocking devices are possible using metal surface. Metal surface is an array of the nano antenna. And I believe that nano-imprinted lithography is the best way to fabricate or replicate the metal surface. Well, the left picture is about the conventional optic lens. And it is bulky, and it's determined by the Snell's law. And right picture is the metal surface. On flat surface, there is the array of the nano antennas. By adjusting the shape and array of those nano antennas, this surface, so-called metal surface, can do many functions, such as lens or hologram or optical cloaking device. Here is the example of the metal surface. All this is a nano antenna. An array of the nano antenna is a metal surface. By adjusting the angle or by adjusting the diameter or by adjusting the rotation, we can control the wavefront of the incoming light. And what we need is the 0 to 2 phase delay with one set of the nano antenna to make those functions. Well, let's move to the nano-imprinted lithography. This is a very simple technique. Well, think about when you need to make some pattern of the functional material. What you have to do is depositing the functional materials, then photoresist deposition, lithography, and etching process is required. However, if you can do some nano-imprinted lithography, just coating the material and imprinting, all those things can be done by a single imprint step. So it gives us a very high throughput and you can reduce the waste of the resources. Well, nano-inflammatory therapy is very old technique. Well, here is a stamp, and we put some imprinting, and this is the patterned product. This is the Korean rice cake, traditional one, and this is traditional Korean cookie. The surface have very beautiful patterns. I mean, people using such an imprinting system. So I like to say that imprint is the old technology, but still very powerful. We can control the size of the pattern as small as 10 nanometer. So here's a substrate, and I have a resin, imprint resin, and stamp. Stamp means the one have some surface protrusion pattern. While pressing the substrate and a stamp, the cavity of the surface is filled with the imprint resin. During the time, we can do UV exposure or applying the heat. The liquid phase resin turn out to be the solid phase. After that, we detach the mold, then we have a nice pattern. Because whole process is very simple and very high resolution is available, nano-inflammatory therapy is the best technique to mass produce the metal surface. Here is some example of nano-inflammatory therapy. Here is the 8-inch master silicon stamp containing 15 nanometer line and space pattern. And this is another 8-inch replicated polymer template. In this polymer template, 15 nanometer line and space patterns are well defined by single-step nano-imprinting lithography. We can use polycarbonate, PMMA, polystyrene, PVC, any kind of those polymer materials can be used for this purpose. Well, this is a silicon mold containing surface protrusion pattern. We can transport this nano pattern to flexible polymer. Then, using this flexible polymer, we can convert this nano pattern to non-flat surface. Because nano-inflammatory therapy is not optical process, by simple physical contact, we can transfer the nano pattern on non-flat surface. And another thing of the nano-inflammatory therapy is that we can do some material science. By mixing the high reflective index materials such as titanium oxide nano particle into the imprint resin, we can adjust the reflective index as we want. And at the same time, we can make some nice patterns, nanoscale patterns, nano to micro scale. This is the nano dot array. This is a high aspect ratio pattern. This is the micron size micro lens array pattern. We can choose silicon wafer as a substrate, or flexible polymer film, or glass substrate. So, using nano-inflammatory therapy, we can fabricate the nanoscale pattern of any material to any substrate. Well, let's move to the AR, VR, virtual reality and augmented reality. The left picture is a very famous Pokemon Go, which is the first augmented reality game. And second one is the virtual reality assisted surgical training. Because it's very difficult to get some cadaver, so people have some trouble to deliver the surgical experience. But using this virtual reality technique, you can do whatever you want to do. Due to such a powerful application capability, AR, VR becoming very popular and also becoming very important. However, what is the current biggest issue of the AR, VR in terms of the hardware? It's very simple. The AR, VR display is very heavy and difficult to wear, and it's bulky and uncomfortable. All these problems are caused by the limitation of the lens. Because conventional lens is bulky and heavy, and such a devices need to have some series of the lenses, whole system becomes bulky and heavy. And another thing is the performance. The image quality is not high enough, and viewing angle is quite narrow, so it's difficult for us to get deep into the virtual world. This problem is also caused by the limitation of the lens. If you can realize the metal lens, you can shrink down its form factor, and you can increase the efficiency. So we can make some very nice and small and highly efficient AR/VR devices. This is a conventional lens, have some millimeter scale. This is a Fresnel lens. It's much thinner. It's about hundreds of micron. However, it has poor performance. But if we can realize the meta lens, we can scale down the thickness of the lens as small as 2 micrometer. That means we can decrease its form factor to 1,000 times, more than 1,000 times. So meta lens is the key solution for AR/VR display. And how we can make some AR/VR display lens? Well, what you need is a silicon master template. From this master template, you can make some polymer replica. On polymer replica, you can do some high refractive index nanomolding materials, such as mixture of the UV resin and titanium oxide nanoparticle. Then imprinting gives us a metal lens. It's very simple, single-step process. And how we can make some high refractive index nanopatterning material? We choose the silicon or titanium oxide or gallium nitride. Those are high refractive index material. We can make this bulk material to nanoparticle. And disperse those nanoparticles into the liquid phase imprint resin. Then we can have two things. One, high refractive index. Two, nanopatterning capability. So we can have the refractive index as higher than 2.0, and also capability of being used in the nano-imprint lithography. Well, this is an example of the meta surface. Well, this is the silicon master template. You can see some array of the nano antennas. And this is the replica. Then using this replica, I rebuild the meta surface using the titanium oxide imprint resin. So if you compare this picture and this picture, it's identical. Well, this is the metal lens formed on the glass substrate. This is the metal lens formed on the conventional lens. And this is the same thing formed on the flexible polymer substrate. And bottom one is is hologram image, 3.141592, ... So it clearly shows that titanium oxide metal surface was formed on a glass curved surface such as a lens and flexible polymer film very well. This is another example. This is the optimized master mold. And this is the replicated nanoparticle composite metal surface. I mean, from using this one as a master template, this one is imprinted. And this is encode hologram. The tiger head is the emblem of the Korea University, and this one is the emblem of the POSTECH. And when you're applying some 450, 532, and 635 nanometer, it can create a very nice hologram image. So hologram type metal surface was successfully fabricated by imprint lithography using high refractive index imprint resin. This is another example. I have a master mold, and from this master mold, I can replicate the polymer template. On polymer template, I'm coating the titanium oxide resin, then do imprinting, and finally we have a metal surface. If I have one master, I can make some millions of the metal surface using imprint lithography process. And when it's changing the diameter of each nano cylinder, we can change its phase from 0 to 2 phi by adjusting the diameter of the nano cylinder from 150 to 400 nanometer. And it has the quite low K value and also high N value. So it's very suitable material for lens application. And this is the imprinted hologram type metal surface. You can clearly see the series of the nano cylinder have varying diameter. And this is the hologram image. The left one is the hologram metal lens formed on the glass substrate. Middle one is the formed on a flexible polymer substrate. And third one is the same thing, formed on metal surface, formed on a surface of the lens. And when using the green laser or blue laser, the red laser, you can clearly see some hologram image, NRF. And another thing is the meta lens, not the hologram type. This is the master template, replica, and imprinted meta lens. Same process was used. And I just measured the performance of the meta lens. With 450 and 532 and 635 wavelengths laser, the meta lens have some focal size of the 2.4, 2.0, 1.7 millimeter of the focal depth, and this is the focal depth, and I think, I'm sorry. This is the focused image, so you can simply see the focus size. It's very small. So in terms of the 532 nanometer case, the focal spot size was a 2.8 micrometer. And that value is very similar to the theoretical value of the perfect lens, which has the 2.4 micron. So I like to say that the meta lens I fabricated using the Nano-Inflammatory Therapy, its performance is very close to the perfect lens. And this is the cross-sectional SEM figure of the meta lens structure. And you can clearly see some nanoparticles. And nanoparticles are well connected with the polymer resin. And its refractive index is somewhere between the bulk silicon value and conventional imprinted resin value. This one is the middle between this amorphous silicon bulk material and imprinted resin. And this is the silicon's extinction coefficient and imprinted resin's extinction coefficient. My imprinted resin has some middle value. So it also has some, by adjusting the diameter of the nanocylinder from 250 to 650, I have 0 to 2 pi of the phase change. And incoming lights are well defined by single nano antenna based on the simulation. So here is the example, the experimental result. This one is the SEM image of the master mold. B is a master mold, and C is the polymer replica, and D is the imprinted metal lens. Here is the digital photograph of the metal lens. I just using the NIR vision system, and I replaced the conventional NIR lens to the metal lens. And here is the metal lens, and I have aperture, and I have a cutoff filter and light source. Then I take the image of the bearing aperture size. When I have a 4 millimeter of the aperture size, I have best picture quality. So using this optic setup, I took the visible light image and also NIR image. You can clearly see that this is a human hands, and this is the same thing. But you can see some blurred lines because I used the 940 IR image. This 940 wavelength IR, human bones and muscle structure, those can pass through. However, it is observed by the red blood cell. Because of that, I can clearly see some veins and the blood lines from the IR image. So let me summarize my presentation. Metasurface can control the phase and amplitude of the incoming light effectively, and any kind of hologram or lens can be made using metasurface. 2, nano-inflammatory therapy can fabricate nanostructure over large area with low process cost. Thus, it is the best technique, best method to mass produce the metal lens. 3, high refractive index nanoparticles such as titanium oxide, amorphous silicon, or gallium nitride was dispersed in liquid type imprint resin. Using this material, various kinds of the metal surface were fabricated successfully using nano-inflammatory therapy. Thank you very much. Well, let's move to our third presentation. After the third presentation, we will have a brief time to discuss about the previous presentations. Our third speaker is Dr. Jonathan Taylor, head of the Data Management and Software Center division at European Spallation Source, ESS. His presentation topic is the European Spallation Source, current status and the future opportunity. Please welcome Dr. Jonathan Taylor.
So we're going to presentation mode, and I'm Jonathan Taylor. I work for the European Spallation Source with research infrastructure in Sweden and Denmark. I'm the head of the Data Management and Software Center, but I'm going to give you an overview of the project in its totality. With this kind of outline, what the ESS is and why we're building it, the current status, where we are right now, and some future opportunities in the next couple of years. As an aside to this, I put my slide link to the Dropbox where my slides are in the chat for this Zoom, so please take a look. So European Spallation Source, it's a high power spallation neutron source facility, a research infrastructure. It's being constructed in Lund in southern Sweden, and it will be the third high power source of its type in the world. So currently there are two existing high power spallation sources, one at Oak Ridge National Lab in Tennessee in the United States, and one at the Japanese proton research infrastructure complex in Tokai in Japan. And then obviously there's a map there on the screen. There's many other neutron sources in the world. Some of them are spallation sources, some of them are research reactors. Of course, there's the Hanaro Center in Korea as well. And the ESS is very much it is exactly like these research infrastructures. It's a user facility to provide neutron science techniques to the broader research community. With the interesting difference that it's a high power spallation source, and that brings significant opportunities for material science and life science research. So what we are is a facility that will be the brightest source of cold neutrons worldwide. We have the highest brightness of neutrons from the 3 to 10 angstrom bandwidth out of all of the neutron facilities. We will be a world-leading research infrastructure because of that, and ESS is a user facility. It's business cases to enable the researchers to visit and get access to instrumentation to perform neutron scattering experiments. The science case for ESS is capability-driven. We are aiming to perform experiments with our instruments which cannot be performed elsewhere in the world. And there's the examples there, really: small samples, high throughput kinematic studies, complex sample environments, automation, and all the rest of that. So it's a capability driven facility. On a slide, ESS looks like this. We are a European Research Infrastructure Consortium, ERIC. That's the type of organization that we are. The budget for the construction of the project is 1.843 billion euro. We have 13 partner countries as part of the ERIC, and we have a lot of in-kind technical deliveries from 13 partner countries. Many of those countries are making or are parts of the consortiums which build the neutron instruments, which I'm going to speak about in a little while. The facility will be has a 600 meter, 2 megawatt proton accelerator. It's the highest power proton accelerator on the planet when it's constructed. So there's a proton accelerator, a five ton rotating tungsten gas cooled target, and then we have a very optimized moderator reflector system comprising of pancake moderators, and these things pictures of these things are available also on the internet. Pancake moderators of 20 Kelvin hydrogen and 300 Kelvin water in some specific orientations such that the instruments can work in a bispectral mode. So cold and thermal neutrons are available to a number of the instruments. And in the construction phase of the project, we build 15 world-leading neutron instruments. So here's a render of the facility. It's very big. The accelerator, you can see there, is 600 meters long, and then the target station and experimental halls are of the order of 150 to 200 meters across. So it's a very big facility. Here's the reason why it's so big is to have neutronic performance, which is comparable actually to time averaged the world's highest power neutron research reactor, which is the ILL in Grenoble. So you can see on the bottom of that graph, the ILL at 57 megawatts has got a time average brightness there, and you can see the long pulse ESS at 2 megawatts averages out to have the same neutron time average flux as the ILL, and this really shows why ESS is going to be such a powerful research infrastructure, because it provides some high instantaneous brightness, which is quite important for time of flight neutron scattering, and the high instantaneous brightness is comparable to even megawatt short pulse spallation sources, but it gives also the possibilities of shaping the pulse to either optimize for resolution or to take the full pulse and optimize for flux. So there's a great amount of flexibility in the instrument suite to allow for that. And this is a render of the instrument suite. So you can see the building there in the middle. I don't have a pointer, unfortunately, but you can see the building in the middle where the instruments radiate from is the target station building, and then we have 3 instrument halls, one on the left, one in the middle, and then one on the right. The long instrument hall is 160 meters long, and the size of the facility is actually governed by the neutronic requirements of having a long pulse spallation source to do time of flight neutron scattering. We are building 15 world leading instruments, and you can see names of the instruments there and the flags of the countries who are parts of the consortiums. And really, it's not actually flags of countries, it's where neutron centers in Europe reside, because all the instruments are being built by existing neutron centers in Europe, of which there are many. So we are building a full suite of instruments, which covers large-scale structures, so SANS, reflectometry, and neutron macromolecular crystallography. And there's a small table there with the instrument names, and the ones in bold are the ones which come in the first tranche of instruments due to start in 2023. So out of that, we have a SANS machine called Loki, a reflectometer called Estea. And I'll talk briefly about these, because from the first 2 presentations that were made this morning, these are instruments which are really very relevant for looking at large-scale structure systems, either in life science or hard condensed matter. So Loki is a broadband SANS machine. It has the widest Q range of a neutron small angle neutron scattering machine on the planet. That's why we're building it. And Estea is a high performance neutron reflectometer. And both of those things together are essentially designed either to look at SANS or grazing incident SANS if you configure Loki to be in that configuration. So they're actually very relevant for the previous speaker's talk on imprinting nanolithography systems. Then we have some single crystal diffractometers. Magic is the first single crystal diffractometer. A powder diffractometer, which is the kind of workhorse of any neutron source, called DREAM. It will have the highest resolution, it's the highest resolution powder neutron diffractometer thus designed. 2 instruments for imaging and engineering, because that's a specifically important use case for neutrons, and a spectroscopy suite comprising of 5 spectrometers, and the first 2 online are C-SPEC, which is a direct geometry chopper spectrometer, which is a workhorse inelastic machine, and Bifrost, which is a high performance extreme environment spectroscopy spectrometer. So here's a table, and I'm not going to talk through this because there's a lot of information, but if you take a look at the slides offline, the instruments are designed essentially to be world leading with the 2 megawatt baseline of ESS. And there's some performance comparisons between the ESS suite and the suite of instruments at other world leading facilities. We are very competitive. Obviously, you'd hope that would be the case. The current status of the project then is that we are 73% complete. We take the first neutron beam in 2023. We're currently 500, well, just over 500 staff, and those staff comprise of 57 nationalities. We did the groundbreak in 2014, and there's a picture there of the facility as it looked, I think, at the end of October. When I joined ESS in 2014, that actually was a field in Lund. There was nothing there. So we have come a very long way. It is a greenfield project, which has its own challenges and also rewards. So then briefly onto the opportunities. I'm going to talk briefly about the use case of diffraction, SANS and imaging. So the DREAM diffractometer is going to be the world's highest, has the highest resolution for a neutron diffractometer, and it will be available day one at ESS. And there's an idea there of the early day science case, which we aim to look at. But if you know anything about neutron scattering and or X-ray diffraction, you know what you can do with a diffractometer. DREAM is designed essentially to provide both powder diffraction and single crystal capability, and also texture. It has a broad detector coverage. SANS, or small angle neutron scattering, low-key again is world leading on day one, and the idea is that one can look at complex life science questions. It is in principle designed as a machine to look at in the life science and soft condensed matter areas. Things like photo-switchable worm-like micelles or fluorescence materials. The idea that low-key has a very, very high flux, something of the order of 10 to the 9 neutrons per second, which is a very high flux of neutrons. Allows you to do kinematic studies almost at the timing resolution of the facility. So the ESS facility is a pulse source. It runs at 14 hertz, and in principle, one can, with instruments with a very, very high flux, look at kinematics at the timing resolution of the facility. So kinematics at 14 hertz, and that is certainly something which is very new for a neutron facility. At the time, so imaging is for neutrons now becoming very, very important, because it is a very accessible way of using neutrons for the user community. So it provides both very, very impactful scientific information for a broad range of science cases, and one of those is these kind of high societal impact preservation examples. And here's a picture of a ship called the Vasa, which is a very famous ship in Sweden. And of course, people that are in the business of doing these kind of preservation or running museums are very interested in understanding how things were made and how things age over time. And neutron imaging, as it turns out, is a very useful tool for that, because it's very penetrating and it's rather non-damaging. And this is one idea of looking at the way the Vasa was built and how things which were made of steel interact with things which are in principle made of wood. So that's a very interesting thing. Going on to more imaging for engineering and imaging and engineering. ESS is a time of flight facility. So it runs in this concept of time of flight, which is actually quite powerful. And one can do on Odin, which is the imaging diffractometer, time of flight imaging experiments, which is really where you take time images as a function of time and reconstruct those to understand the phase segregation in large components or in large components. So this is important for a number of things, because you can look at stresses and strains all in real space, which is a very accessible way of presenting information to the user community or to non-expert users. And this then opens up all sorts of interesting things for what is now modern additive manufacturing processes, where strain in these processes is actually very important to understand how to perform additive manufacturing in a good way. The other side of a research infrastructure, of course, is support for users. And the idea is really for ESS is that we aim to make neutron research accessible for non-expert users. That's the objective of any research infrastructure, really. And we have some novel things for this. One area, of course, neutrons, if you're aware of how the technique works, are very, very sensitive to hydrogen, which is in some cases a good thing. But in some cases, it's quite challenging because hydrogen has a very high incoherent cross section. So you lose a lot of the coherent sensitivity which you can have. And one way of getting around that, and one very powerful area of neutron research per se, is isotopic substitution. Of course, that's a very complex and challenging thing to do for a non-expert. So ESS has been running a platform called DMAX now for over a year, which is a deuteration service. It works like a peer review access to a research infrastructure, in that you can ask our scientists for a range of services, and the range of services are there. So biological deuteration for things, for protein crystals, for example, chemical deuteration, that's deuteration of small molecules. And then from the biological deuteration, actual protein synthesis. Protein macromolecular, neutron macromolecular crystallography is not as wide-ranging and maybe as impactful as its photon source counterpart, but it is actually very powerful. And one of the challenges is making large volume millimeter, half millimeter cubed protein crystals for NMX, neutron macromolecular crystallography, and we offer a service for that. That's very important, and that actually is, this service DMAX is running right now, just as a matter of interest. We also have the thing that I am responsible for, the Data Management and Software Center, and there we are essentially aiming to provide a data analysis service. I mean, I think this is the take-home message. One of the challenges really for doing neutron scattering, like with any research infrastructure, is making sense of the data once you've taken it. So we aim to provide a service for users to help people with their data analysis. We are very involved in what in Europe is called the European Open Science Cloud, which is fair data and open science. So something that we're big proponents of. And of course, we have some compute capacity to do all this. In the future, we are building 15 instruments right now, but we are going to build out to 22. So that's going to be the full reference suite of instruments by the end of 2030. The accelerator is going to upgrade from 2 to 5 megawatts. This is something which is quite important. That becomes even higher flux of cold neutrons. It's important to know that the 5 megawatts was the baseline specification back in 2013, and then there was a considerable amount of work to optimize the moderators such that at 2 megawatts they had the same performance at 5 megawatts. So the 5 megawatt performance of ESS will be actually astoundingly powerful. For that, there's a current project running right now, which is funded by the European Commission, called HINES, which is evaluating additional upgraded moderators for the facility. Facilities like ESS really rely on the moderator subsystems and the performance of those, and that's something where ESS is really is state of the art when comparing the moderators across other neutron sources. The other thing of interest, actually, I've spoken a lot about neutron scattering, but the reference design of ESS has space provision for particle physics experiments, of which there are some already expressions of interest for either neutron decay or neutrino oscillations experiments. This is actually a very major upgrade of the facility over, certainly not over this decade, but in the future. This will be something which I would imagine being built in the next 10 to 15 years. So that's my summary. I'll end now saying ESS is a next generation neutron user facility. We are the largest European investment in neutron science since the design and construction of the Institut Laue-Langevin in Grenoble back in the late 60s, early 70s. And the facility is going into neutron operations in 2023. Thanks very much.
Thank you for your presentation. Now we have a short time to discuss each other's presentation. Anyone have a question? Feel free to participate. If not, I have one quick question to Dr. Taylor. So you said that the ESS will be operational, functional on 2023, right? And can I make a reservation?
Could you make a reservation right now? No. But yes,
don't be
I mean,
serious, it's a joke. Yeah, so I hope everything will go on very well.
Thanks.
Yeah, and I have one quick question for the MIFAB. What kind of lithography system and what is the minimum feature size of the MIFAB can do fabricate?
The minimum feature size to fabricate in the E-beam, we have in certain structures down to, I think, down to a couple of nanometers for the E-beam, high resolution. Then we have other technologies to put on very thin layers that is basically atomic, each for single atomic layers. And depends on specific material systems.
Okay, understand. Thank you. Any other questions?
Thank you.
Yes, go ahead.
Yeah. So thank you for your presentation. So actually, I have visited my fab. Actually, I have visited Chalmers since last 2 years. So actually, I also have experience in using the my fab. So it was really cool, and they have really nice facility. But this is actually my feeling that there are still some rooms for the new facility, and also there are some kind of old machines. Maybe they require for the renewal. So I have a question about the MyFab. So do you have any plan for the new facility or some kind of renewal of old machine in MyFab, especially for the MC2 at Chalmers?
Yes, thank you. We have a grant. We recently received a grant from the Research Council, so we can make investments for about 10 million euros in new equipment for the whole of MIFAB. And we definitely plan to upgrade, for instance, E-beam resources on the long term, as well as we recently made in Uppsala an investment on 3D lithography. This is part of a larger commitment from all the universities. This is a very important contribution, but in addition to that, also the universities have plans to upgrade equipment, and also then, of course, equipment has to be renewed over the years. That is also part of such a program. That is a very important question, because there's so many researchers that depend on functioning tools, and having 700 tools, they are in different stages, of course. And tools, there are not the most important is the process chain of processing steps you perform. So a tool can then rely on, a process can rely on maybe 20, 30 steps sometimes. So you need to have the whole chain in well shape. So that's a very important task to renew investments in such an infrastructure.
Okay, understand. Any other question from the Sweden side? If not, it's time to move to the second group. In the second group, we have 3 more speakers from Korea and Sweden. Our first presentation is by Byung-il Hwang, professor of the Jungwon University. The presentation title is Machine Washable Conductive Silk Yarn with the Composite Coating of AG Nanowire and P.PSS. So let's start with Professor Hwang.
Nice to meet you. My name is Byung-il Hwang. I am an assistant professor at Jungwon University in the School of Integrative Engineering in South Korea. First of all, it's my honor to have a chance to present my research work in this important event. I'd like to also give my gratitude for all the participants in Sweden and Korea, as well as for all the involved people to prepare this event. So my presentation title for today is Machine Washable Conductive Silk Yarns with the Composite Coating of Silver Nanowires and P.PSS. This is the result of a collaboration research between my group and Professor Miller's group in Chalmers University of Technology in Sweden. Before giving the details of the research work, I'd like to first highlight the increasing market size of the wearable electronic devices. According to the market forecast, the wearable electronics market size is $37 billion in 2020, and the size will increase in 15.9% in every year. The wearable electronics are definitely considered as a mainstream of post-smartphone business. Currently, the wearable devices are mostly dominated by wrist or eye wears, but it will be developed as a clothing style in the future. And for the clothing type of wearable devices, the conductive fibers will be an essential component for realizing that kind of clothing types of wearable devices. Therefore, there are many researchers, including me, to develop the reliable conductive fibers for wearable devices. Depending on the structure, the conductive fibers can be categorized in 3 different forms, which include single metal or polymer fibers, or conductor-coated fibers, and conductor-embedded fibers. Those 3 fibers have different pros and cons, but the washability is a key for the reliable conductive fibers in any forms. So while I'm trying to enhance the washability of the conductive fiber in Korea, I had a chance to read this paper, where the authors are at Chalmers University of Technology in Sweden. Actually, this is a really cool research result where they use the natural silk as a core material for fiber and provide the conductivity by using conductive polymer, which was PEDA-PSS. Since the natural silk surface had a pH 4 value, which is the isoelectric point, it can possess the net positive charge, which provides electrostatic attraction to the negatively charged sulfonate groups of PEDA-PSS. By doing so, they can achieve the wonderful washability of the conductive fibers. Actually, that was a really wonderful result. However, at this point, I have a question that they can further enhance the conductivity of their fiber because their fiber showed relatively low conductivity, which was below 15 GMS per centimeter. Actually, at the moment, I was intensively working on silver nanowires and also publishing quite many papers about silver nanowire-based electrode. As silver nanowire is a hair-like structure of silver in nanoscale, and they can be formed as a network structure, thereby providing high mechanical flexibility as well as an excellent conductivity. Also, they can be easily coated on various surfaces with simple coating process. Thus, when I read the papers of the Chalmers group, I had a simple thought. If we can apply silver nanowires to their PEDA-PSS fibers, then we can enhance the conductivity of the fibers while keeping the excellent washability. The silver nanowires have a definitely much higher conductivity compared to the PEDA-PSS. Also, I thought that if I could get a chance to work with the Chalmers research group, it would be really cool. Unfortunately, I couldn't get a chance to do that. In Korea, there were research funds from Ministry of Science and ICT and National Research Foundation of Korea to financially support the collaboration research between Korean team and EU ERC team or Sweden team. So I personally contacted to the Professor Christian Miller at Chalmers. He was leading the research team in the paper and get approval to work with them. So I applied to the funding and got a chance. With the kind support from Ministry of Science and ICT and NRF Korea, and also from Professor Miller's group and Chalmers University, I have visited Chalmers and did the research. And also one of my students could have a chance to visit them and is doing collaborating works. So at this point, I want to give my gratitude again for all people who supported this research. With their support, we could realize our ideas in the realistic forms. Really, we did quite intensive collaboration and had a nice result. We could develop the machine washable conductive silk yarns with excellent conductivity by applying silver nanowires. And with this result, we could publish a quite nice paper in ACS Applied Materials and Interface in 2020 with the title of Machine Washable Conductive Silk Yarns with the composite coating of silver nanowires and PSS. Actually, there are a few more researches in progress together with Professor Miller's group and also the other group in Chalmers, but today I'd like to only give details for this result because of the time limit. So, as briefly explained in previous slide, the concept of this research was to insert silver nanowires between the core silk filament and PSS coating. For this, the pre-washed silk yarns were deep coated with silver nanowires followed by the post-annealing at 180 degrees C for 5 minutes. And as a final step, the silver nanowires coated silk yarn was coated with the PSS followed by drying using heat gun. As can be seen in the scanning electronscope microscope image in the below, the overall silk yarn surface was covered with the silver nanowires, and PSS also covered silver nanowire and silk surfaces. The conductivity of the fibers could be controlled by the number of deep coating process. As you can see in the top left figure, the conductivity was increased as the deep coating number increased. In addition, the conductivity could be further enhanced by the post-annealing process. As you can see, as the post-annealing times increase, the conductivity also increased together. So, during the post-annealing process, the silver nanowire networks formed the junction that supported the electrical current flow, thereby enhancing the conductivity. With the combination of the deep coating process and post-annealing process, our conductive yarns showed about the 320 Gms per centimeter of conductivity, which was much higher than those of PSS only fibers, which was the previous developed one in Chalmers. So this is the machine washability test result. The blue dots show the result of commercially available silver-coated silk yarns, which is the Shieldx, and red dots show the result of our fibers. So the results show the commercial yarns show the rapid degradation of the electrical property only after 2 cycles of washing. However, our silver nanowire and PSS coated yarn show no significant increase in resistance even at 10 cycles of washing. So clearly, our yarns showed much better washability compared to the commercial ones. From this result, we could confirm that the machine washability, which was resulted from the attraction between the PSS and silk yarns, was kept even after inserting silver nanowires between the PSS and silk yarn surface. So to further confirm the reliability of the conductive yarns, we tested cyclic bending test and also tensile test on our conductive fibers. The top left image showed the resistance change of the conductive fibers during the cyclic bending. So that result showed that our fibers showed less than 30% increase in resistance even after 300,000 cycles of bendings, while only silver nanowire coated yarn showed nearly 2 orders of magnitude increase. This top right image shows the stress strain behavior of our conductive yarns. They showed below two-fold increase in resistance at the rupture strength. And those results show that our fibers also had a nice mechanical reliability, as well as keeping the wonderful machine washability. Lastly, we demonstrated heating fabric and heating socks using our conductive fibers as a Joule heating element. The heating fabrics, as you can see in the left image, the heating fabrics achieved high temperature upon a small voltage of about 2 or 3 voltage. This clearly showed the potential of our conductive yarns for the Joule heating element of wearable devices. So, in summary, as a result of collaboration between our team and Prof. Miller's team at Chalmers, we could develop machine-washable, highly conductive silk yarns using silver nanowires and PWS composite coating. Our fibers really show the high electrical conductivity, as well as an excellent machine washability and mechanical reliability. We believe our development will help to accelerate the commercialization of robust wearable electric devices. For the next step, we are in progress to develop the fiber-based sensor or energy harvesting devices using our conductive yarns. And I hope later we can have a chance to present this result again. Okay, so thank you for your attention, and I would like to welcome any question about my research and the collaboration behavior between our group and the Chalmers. And this work was financially supported from the National Research Foundation of Korea, which is funded by the Ministry of Science, Information and Communication Technology. Okay, so thank you for your attention. Thank you.
Thank you very much for your presentation, Professor Wang. Let's move to the fifth presentation. The speaker is Dr. Tunison, who is the Life Science Director of the Max4 Laboratory at Lund University. She will talk about the Max4, the first MBA-based synchrotron. Let's welcome Dr. Tunison.
Very much for the invitation to give this presentation. And I will present Max4, the status, and some research that we have been doing. So to start with, what is Max4? And I start my presentation. So Max4 is a new high brightness synchrotron light facility next door to the ESS, where we already had a presentation on. It's a national laboratory in Sweden, but we are very much not limited to only researchers from Sweden. In fact, we welcome researchers from all over the world as long as they can do very good science. I also would like to stress that although we are very, very new, we're also the successor of a long tradition of accelerator design and development in Lund, because we have had MaxLab, a previous synchrotron in Lund, which has been functioning for more than 30 years. Max4 itself is the first MBA-based light source, and I will come back to that, what that actually means. To give an oversight of our facility, I show this picture from the sky. We are based on a long linac that is placed, that is placed underground, starting at the electron gun, going 250 meters to our big ring, and then continuing for another 100 meters to a short pulse facility where we have a dedicated beamline for time-resolved measurements. This linac doesn't only serve the big ring, but also a smaller ring, and these have slightly different characteristics. The big ring is about 500 meters in circumference and runs at 3 giga-electron-volt. The smaller ring is only 96 in circumference and it runs at 1.5 giga-electron-volt. The facility is hosted by Lund University, but it's run by Lund University and the National Research Council in Sweden, Vetenskapsrådet. As I said, it's a national laboratory, and we run as an open access facility. That means that if you have a proposal of high scientific value, you can get access to a proposal system where science is the first thing to be reviewed. Currently, we are about 250 staff members. As I said, we are the first facility that runs with an MBA. An MBA stands for multi-band accrement. And in our design, we have 7 of these accrements. The advantage of using these accrements is that by the many magnets, we can focus our electron beam that goes through the accelerator very, very nicely so that we get a very, very small emittance. And this emittance is linked to the brilliance of the beam. I should say that the concept of the multiband accremet was not something developed by Max IV. This was a proposal by Dieter Einfeld already in the 1990s. The big problem, however, was that with conventional technology, it would be an impossible design to make. It would make that the synchrotrons would have to be kilometers in circumference, and this would be extremely expensive. What happened at Max IV is that we could actually minimize the technology for the magnets. So we actually made the magnets really small, and we actually formed units where several magnets are in the same unit, and the whole ring is built out of these units. And by working like this, we can actually build a normal sized synchrotron, but with a very high amount of magnets that leads then to an increase in brilliance. And if you compare Max IV with 3rd generation sources, you can clearly see that the brilliance of Max IV excels that of 3rd generation synchrotrons. Also in this picture, you can see our own journey. Our old lab, the Max II ring, which was the most bright synchrotron in the old lab, is shown in the picture at the bottom. And we have made an enormous journey to our new peak at the top. How does it look in reality? This is a picture of a conventional synchrotron, and you can see the very big magnets and how filled up the synchrotron tunnel is. In comparison, here we have Max IV, and the magnets are just on top of the big blocks of concrete here, and the whole, and you can see how much more space we have because of the minimalization of the magnets that we have achieved. Of course, things happen after that, and many other facilities, when they saw that our concept was actually working, started to really think about implementing this as well. And you can see we were the first facility to come online using this technology. But after that series, a new synchrotron in Brazil has come up that uses the same technology. The ESF has made a variant and is now operating as well. So it has upgraded to a similar system, and other facilities are in line for their own designs and upgrades to go over into this technology. So Max IV has really been a technology inventor here that has driven the field forward. What does it mean for the users? Because at the end of the day, this is of course our main mission. We are a user facility, so we really want to give the best beam to our users. And by implementing this new technology, we actually have created an excellent source for micro to nano beams. It's an excellent source for flux-hungry experiments, such as time-resolved experiments or things such as resonant inelastic scattering. Because we have a quite high amount of coherence, this facility will be an excellent source for imaging experiments, but also dynamics, as you can do by methods just such as XPCS. And finally, I just would like to say that this kind of upgrade really means that there are many possibilities for material and life science that really can flourish at our facility. So the first question is, of course, how did the machine actually work? And as I said, we have actually 3 machines. We have the LINAC, we have the 1.5 ring, and we have the short pulse facility at the end of the LINAC. And all of these are working really, really beyond expectations, I would say. So these are the hours of delivery and the availability during the last periods. And you can see that we are at the moment over 97. Actually, in the case of the 1.5 ring, we are now over 98% availability, which is for a facility of this age that Max 4 is really extremely well. What I don't show is actually the stability of the beam, which is also very important. And we have also achieved a really, really good stability, which makes it very good for the beam lines to actually work with the very small beams and the very small samples that we are addressing. Just a little bit about the things that we can do. In general, as you probably all know, X-rays can look through material. So we can actually look at what we call the invisible. And the things that we can see are things like nanostructure, which we can address by imaging. We can very carefully determine the position of atoms and understand molecules and for example, proteins. And this we can, of course, do by scattering and diffraction. The state of electrons can be studied mainly by methods such as spectroscopy, whether it's X-ray absorption, XPS access, emission spectroscopy. But we can even look at the spin of electrons if we do dedicated spectroscopy, such as X-ray magnetic CD or spin polarized XPS. And all these methods we actually have available in our suite of beamlines. So if we look at our suite of beamlines, we have beamlines that are more dedicated to imaging, ones that are more dedicated to scattering and diffraction, and ones more dedicated to spectroscopy. And we also have beamlines where we can combine techniques. And by that, we can really look at electronic structure or chemical composition, as well as geometric and atom structure at the atomic resolution. If we go to the status of Max 4, we have 16 funded beamlines, a number that we've heard before. And of these 16 funded beamlines, we have currently 9 that are in general user operations. There are 4 more beamlines, including the Femtomax, which is the beamline dedicated to ultra-fast processes at the end of the LINAC, which will become available to the general users in the coming half year. And finally, we have 2 beamlines that are in installation and building phase, and which are slightly later in their phase, which are Micromax and Formax. The other thing I would like to say here is that most of our beamlines are actually financed from Swedish resources. Knut and Wallenberg have been a generous funder for the first set of beamlines. We have gotten contributions from Finland and Estonia to build finest beams. We have gotten further contributions from Wetenskapsrådet and KRW for the next set of beamlines. And then we have 2 beamlines, Danmarks and Micromax, which are paid by public and private finances from Denmark. And finally, we have Formax, which is a beamline dedicated to paper and pulp. It's really looking at structures of cellulose and cellulose fibers, renewable materials, and all those kind of things. And this is paid by the Knut and Wallenberg, as well as a consortium of academia and industry for the operation cost of this beamline for the next 10 years. In the rest of my talk, I would like to single out one beamline to go a little bit deeper into that particular beamline. I felt that it was nicer to do that than to give a very quick overview of everything. And for reasons that become quite visible in a bit, I've chosen Nanomax. So Nanomax is of course a very important beamline for nano research, but it also very much highlights the reasons why this MBA design is really helping our users to do new science. So I think for those reasons, it's quite a nice thing to highlight. So Nanomax is our longest beamline at the moment, from the source, the undulator inside the synchrotron, to the final position at the sample. The beamline is about 100 meters long. It has two end stations with slightly different focus. And the first end station, which is now fully operational, is the furthest away, and the other end station is at the moment under development. It's a nanoprobe where you can do very many different things: scanning transmission microscopy, X-ray diffraction, X-ray fluorescence, and then as well, very importantly, coherent diffractive imaging methods. And especially that technique I would like to highlight. There's also photography and of course, everything you can combine into 2D and 3D imaging. So one of the first things, of course, when you build new beamlines is to do a full characterization. And this is a full characterization of the beam using tychography, and is really, really highlighting that we can produce a very nice nanometer beam with a very high flux, but also that we have a very high amount of coherence in this beam. So our coherent properties of this beam is really, really good. And we were very pleased with this characterization, which has very recently been published in Optics Express. And it shows that the concept that we have been using really works, which is very important. And with this high coherence, you can do quite new experiments. So the following experiment is a quite simple one. It's called nanoparticles, which were floating. So in classical crystallography, you have to do rotations. In this case, these particles were floating with their own small rotations. And by using coherent diffractive imaging, we could actually assemble the coherent diffraction volume such so that we could actually show the image of the full rotating nanoparticle. So this is quite a new thing, and it can actually probably really yield to new types of experiment looking at these kind of nanoparticles, which can be quite important for all kind of processes from electrochemistry to others. And this was a collaboration between Max 4, the group of Jesper Valentin at Nano Lund, as well as Felipe Maya at Uppsala University. And another experiment where you can really see what you can do with this kind of nano beam is an experiment on nanowires. It's again the group from Jesper Valentin at Nano Lund, and in this case, it's nanowires that contain small domains that formed when you do temperature transitions that could be ferroelectric. And these domains, they form at about 80 degrees Celsius. So these nanowires were put into the beam and using again Bragg diffraction, you could really see discrete Bragg peaks where we could use this information to actually compose the images of these nanowires. And it was also very, very clear that these nanowires do have ferroelastic behavior. And it could have all kinds of implementations for ferroelectrics. And this is published in CS Nano. And with those examples, I would like to close my presentation, but not before I thank all people at Max 4 for their terrific work, and especially the Nanomax team, Alexander Björling, Ulf Johansson, Sebastian Kalbfleisch, Mike Kantok, Simone Sala. And thank you for your attention.
And we have our last presenter, Dr. Seung-Cheol Kim from Korea Institute of Science and Technology. The title is a web platform, new research environments for material science. Let's welcome him.
Thank you for inviting me to this excellent event. I am Seung-Cheol Kim from Computational Science Research Center at KIST. Today, I would like to talk about simulation web platform, which is a new research environment in the material science. So when I talk about the simulation platform, people usually think this is a kind of first paradigm of research, which is data-driven research or machine learning. But I am still in the third paradigm of simulation. So the platform I am talking to here is the research tools for the third paradigm. Over the last 30 years, the simulation, including density functional theory, become very popular, and partly because of the very rapid growth in computation power, for example, 1 million times faster during the last 20 years. Many of the research paper, top-cited research paper are in density functional theory. For example, 2 in the topmost research cited paper in whole science field is density functional theory. So it is the most successful and popular research method since the last century. Then, is it really easy to use to you? For example, if you want to include just one figure in your paper displaying DFT data, can you do it easily, for example, by yourself? The answer is no. But still, many things are necessary to do the simulation, including theory of the simulation, software, and knowledge in computer as well. You also need a very expensive and sensitive high-performance computer. But nowadays, you can use computer provided by the government or cloud computers, but you still need years of training to get used to it. So still, computer simulation is something like this formula car, which is very fast and powerful, but only well-trained people can drive, which means it is not very useful to most people. But we want to make simulation program like this usual car, maybe not very fast, not fast as much as the formula car, but it is fast enough. And more importantly, it is much easier to drive. So this is not about the strategy to find the new material, but about how to build a new research facility on the web, especially with many collaborators. So there are 2 types of simulation platform. The one is a method-oriented platform. For example, TFT platform, MD, MC, FEM platform are in this category. There are even commercially available platforms in this field. And the other type of platform is application-oriented platform, or in other words, the thematic platform. This second type provides a comprehensive software tools for the specific application and specific types of material. In the previous slide, I've told you that we were developing truly easy-to-use simulation program, even to the non-expert in simulation. To do that, we made a concept of virtual equipment. You can make an analogy to the experimental facility like virtual STM, virtual AFM. And if we arrange this virtual equipment according to the specific workflow, it becomes a virtual laboratory. And if we do for the specific application, then it becomes a thematic platform. Here are some virtual equipment we have made several years ago. For example, this top left thing is a virtual simulator of STM, which gives you the simulation image of STM from the atomic structure. In this bottom left is a virtual furnace. You are able to simulate the structural change over time in the gas or oxygen condition, and you can finally get the result, get the final structure, which is conceptually similar to the annealing process in the furnace. All of them have very well-defined simple functions and have minimal input parameters used only in the field of simulation. For example, in this virtual STM, user only need to put the voltage and position of the tip, and no more input parameters are necessary. Let me define one more word, the simuloscope. As the telescope shows an object from a distance, the simuloscope displays simulation data onto the real space, just like the augmented reality. It could be a simulator of real experimental equipment, but some of them does not have corresponding experimental tools. For example, in this right bottom figure, it displays the unmeasurable data from the experiment, like charge, stress, or coordination number at each atoms. These four are the simuloscope installed in KIST platform. The stress in a nanoparticle, position, density of states map is just like STS image. And the other one is a D-band center map, which is very important for the catalytic application, and the other one is AFM. All of them can be operated alone, and they can be a part of the platform. So we were in collaboration with Uppsala University with this collaboration program. We developed nano simuloscope and thematic web platform for the catalytic design. Some of the simuloscope in the previous slide I just showed you was made from this collaboration, and they are plugged into the catalysis design platform. We held 4 times of joint workshop in Sweden and Korea, and 3 times of sub or satellite session in the international conference. Several people visited to each site for a while, and we invited each other to European and Asian conference to build a network. Okay. This is the catalyst platform we KIST have made. And the simuloscope we have developed together with Uppsala University through this collaboration programs are installed in this platform. Let's see the left top page. This page have a function to build up the sample, which is the thermally stable in given condition, thermal given condition. If you bring those sample to the other analysis lab, we can analyze it atomic and electronic structure. And finally, if we bring those sample to the performance test lab, then we can test its activity in catalysis by calculating binding energy of the chemicals or drawing reaction diagrams. So compared to a usual simulation program, this is incomparably easy to use. Now let's talk about the collaboration according to the purpose of this meeting. As you may imagine, there are really many simulation tools and programs behind these web pages. And maybe more than the 100 program modules are seamlessly connected behind this web page. And many people joined the development, and they made programs in their own style. So we definitely have to have a rule to make a program, which means a protocol and data format. And we also have to have develop collaboration tools to provide identical developing environment to everybody. The contents management system of website is the solution. So web page have lots of contents, just like image, text box, or menus, or video players. The CMS is the software developing environment to create and managing such contents very systematically. So it provides protocol and standard, and it is a collaborative in nature. So even if the people make their own content independently, there is no problem to others to use it as long as they use the same CMS. So we have built contents management system specialized for the web platform, and we named it Simple after the simulation platform. It provides many contents by default. For example, atomic structure visualizer and manipulator. And it also provides a web page for the platform developers. So everybody go into this web page displays in the right side of the slide, and they work on this web page. So same environments are provided to everybody. Immediate sharing the result is possible even if we work in a distance. So let's see how it works. Let's say our team wants to build a virtual STM like this figure in the left top side. The first programmer makes atomic structure visualizer, and second does the depth controller, and third person make a program to display two-dimensional data. Well, they develop all three independently. Now you, the manager, combine those three contents in the one page, then it'll be a virtual STM. And if the other person made some data graph drawing modules, then one can make a density of states calculation and displaying page by combining other two modules. So it is also possible to make the platform ecosystem if many developers in the globe use the same CMS. The more people use it, the richer the contents, then finally it will be the easier to build platforms. In the last year, we held the hackathon of the web platform development. 33 participants from the 14 universities and institutes, and we have made 10 different platform pages in 2 days. It is surprising because many of them has no experience in this content management system. So we saw the possibility to build up the ecosystem. In summary, I have started from the difficulty of the simulation and suddenly jumped to the simulation web platform, how to build, and the concept of the thematic platform, and finished with the content management system. The thematic simulation web platform is very close to the real. And as I said, method-oriented platform is already commercially available. And in terms of collaboration, for the successful collaboration, good collaboration tools and rules are also important, just like a content management system of the web platform. One more thing I would like to point out. The biggest obstacle in the real development is this. So one day, one guy from the Uppsala University told me that every student wants to lead their own project and nobody wants to support others. And also one student from my group asked me that if we really need to keep on working hardly for this unpublishable work. So this is true. Developing a simulation web platform is a kind of a job, support others, and it is very difficult to get published. The thing is, the student and postdoc the main workforce, And professors and staff scientists, they are more likely manager rather than real researchers. And the students, they need a lot of good paper publication to get a job in the future. So it is very difficult to push them to work this unpublishable work. But actually, when we develop platform, we just need one programmer who is not evaluated by the number of publications. But because of the structure of workforce in the institute, it is very difficult to hire new programmer. So we built a company because of building a company is a little more easier than hire the programmer. And we are still in trouble with developing a web platform, but the situation become much better. And I don't know whether the government official or people in the charge of making research program consider this problem with the workforce. But I hope them considering this problem seriously. Thank you for attention.
Dr. Kim, thank you very much for your presentation. Now we have a little time for discussing each other's presentation. Anyone have a question? Feel free to participate in.
Magnus Fiber here. I have a short question. Yes, maybe I can ask Marilyn and Jonathan to explain who your neighbors really are. It wasn't really clear from your presentation, and I think that's a very key, important piece of information.
Yes, so we are based right outside of Lund, to the north of Lund, and just slightly above us, 900 meters from us, is the European spallation source. So the ESS is really, at the moment, our nearest neighbor. There is actually a piece of land between us and the ESS, which is available for further development. And one of the things that will happen there is that the Nano Lund part of the physics department is going to move there. So part of Lund University will actually build between the ESS and Max 4. And there are also other facilities that will be built there, like common user facilities, like a place to stay over and things like that. And so we are in a part of Lund which is called Brunsberg, where we will get a very nice development in the coming years. Is that answering your question?
Yes, it is. I think highlight that it's simple to, if you want to use both European spallation source for the neutrons and Max 4 for the synchrotrons, you can do it like all in one day. You don't have to travel across Sweden or anything.
Yeah.
It's part of MyFab, so you have access to the full capabilities of MyFab through the Nano-Lund facility.
Yeah. Exactly.
Actually, I have one quick question to Dr. Tunison. I'm here in Korea, and I cannot go to Europe because of the corona situation. But if I like to do characterization of my sample using your very fancy tool set, is it possible I can use it by FedEx the sample to Sweden, and you can do some characterization and send me back the result?
Yes, indeed. So when the COVID-19 really started to hit us, we were actually able to switch over to remote and mail-in experimentation where possible. So our staff have really done a very good job of switching over, and many of the experiments we can do through remote or through assisted mail-in. Now, if your sample would require quite a lot of preparation and so on, of course, this is not possible. But if you have a well-characterized sample, yes, then we're open for mail-in.
In the case, I may need the mailing address of yours to send the sample to you. Okay. Any other comment, question from Sweden side or Korea side?
I actually have a question to the last speaker. You were talking about tools for common software development to really be able to collaborate between the 100 researchers. Could you tell me a little bit more about what kind of tools you are using?
Okay. We have developed contents management system. It is kind of the usual, some specialized contents management system to build a web page. So it is, you can download from the Git, from the website, and you can install on your computer. If your computer serves the web page, then the developer of the web page or a simulation web platform can use such a web environment. The figure I show you in the slide, that is the system installed in our computer, but you also can install it on your computer as well. You simply download from the web and install. But thing is, your computer must be a Linux system, and we are using Docker, which is all the complicated HPC setting. We made it as an image, so you can simply install. It's much easier. It's like installing Windows program.
Actually, I have one quick question to Dr. Kim either. You said that, your research result is used to build a new startup company.
Yes.
Right? So my question is, do you have any successful example of people who using your tool set to develop or to manufacture the new materials such as catalyst or whatever?
So far, the Catalyst webpage, it is not fully open. So we are almost at the last stage of the development. So not many people have used the Catalyst web platform. But the company that I mentioned they serve a simulation web platform for the general purpose. As far as I know, their main user is not a simulation expert. Usually experimental people, they use their platform to simulate by themselves. So in the industrial viewpoint, so far I didn't heard that any successful story for real commercialization of the material, but there are many research papers published by experimental people, and they do their simulation by themselves using the web platform. So they don't ask to the simulation people to do the simulation to others.
So using your tool set?
Yeah, so you can do your simulation.
How many papers are being published?
I don't remember exactly, like something like 10, I think, because the service started just I don't know, I don't remember exactly, maybe 3 years. But one very promising result was like it was last year. Several high school students, they have learned simulation, quantum mechanical simulation of material using that platform, and they made a report to the school. So even the high school student, if they learn something like 3 days to 1 week, they can do quantum mechanical simulation.
Okay, thank you very much. Any further comment or question or anything? If there is no more, let's summarize our.
Magnus,
go ahead.
short one again. So,
No one is okay.
As we said before, we are going to have this meeting between governments soon, and we are hoping to put in some information from VR and NRF concerning the future collaborations. So, material science is a very broad theme. What do you suggest we put for proposals to our ministries about what future types of collaboration we can do within the area of material sciences? Should we keep it very broad, or should we specialize on something like energy, batteries, smart materials, or in general, I would like to hear that from you. Which lane should we go?
I think you mentioned about the energy device, material, and battery. I think those two things are very hot keywords in the material science world in Korea. So I think the Swedish synchrotron and also the neutron scattering system will be built, there should be a long line for Korean researchers to use the equipment. And I really appreciate in year 2023, I just want to be the first line in the long waiting list. So any other comment? Maybe Dr. Kim or Professor Wang?
About the collaboration cases, you may sick and tired of hearing about data kind of things, but the Korean government just started a study to build up some kind of system to collect the data. For several years, it happened just between two simulation people, but from this year, the Korean government, really starts to collect the experimental data kind of things in the national size. For example, in our institute, we already have built some software system to collect all the experimental data generated from our institute, not only the calculation, but all the material, truly experimental data as well. So as far as I know, there is some efforts from the European as well. So I think one of the easiest way to do some collaboration is some relative to the data kind of thing. It's not about the simulation data, but also truly experimental data. So in that cases, as far as I know, the people leading about this field, they want to build up some federated data pond or data lake kind of thing. So in Korea side, we also have several data set or data lake, and European side also can make those some data lake, and can make some federated system. There is the effort that made by the many people over the globe. And Korean government really pushed such things very recently. They made their budget about making some data collecting system is really huge. So I think the European side also can do similar. Thank you.
I would like to hear Jonathan's response to that one.
Yeah, sure. I was going to say, by the way, Dr. Kim, I very much enjoyed your presentation. It's very, very impressive what you've done with the VREs. That's very exciting. So yeah, in Europe we have the same kind of concept really. It's called the European Open Science Cloud, but it's a data lake. It promotes fair, findable, accessible, interoperable, and reusable data across themes, across thematic clouds. And across the entirety of the research community, in the kind of area where we are, where I am, in neutron scattering, there are some specific projects. One is called the PANOSC, which is the Photon and Neutron Open Science Cloud, and there's a sister project to that called EXPANDS. That doesn't matter why there are two projects in principle doing the same thing. That's just a matter of the way the European Commission organized the funding. But it really is a big thing actually in Europe. Data management and FAIR is becoming very important for the research community, because the literature, the publishers of academic journals are now really asking for some more provenance on the data. And just, everybody knows that when you do experiments, it's important to do a good experiment and to ensure that you can make you have some reproducibility, and all of these kind of data management aspects fold into that. But anyway, from the European Open Science Cloud side of things, it's quite a it's quite a big project. Well, it's quite a big movement. It's somewhere nearly, I think, if you take the funding from Europe, from Horizon 2020, and then into Horizon Europe, which is two periods of European funding, it sums up nearly to €1 billion in activities around data management for research. And one of the things that the EOSC, the European Open Science Cloud, understands is that the European movement has to connect and federate with other worldwide, pan-European movements, of which there are, a number, and the working career has just been described. So I think that the collaboration, on this is, it would be very exciting.
Mhm.
Okay. Any further comments? Then let's thanks for all presenter and participants from both Korea and Sweden. Thank you very much, everyone.
Thank you.
And let's keep in touch via email.
Yes.